Hello, I'm Ryan Avril,
And I'm Erick Rossi de la Fuente.
and this is our project on star spots on LO Pegasi. So what are star spots? Star spots are dark spots in the photosphere of a star. The photosphere is simply the visible layer of the sun, or star. Star spots on our sun are of course called sunspots. They can vary in size depending on how fast the star is rotating. The faster a star rotates, the larger in size the spots can be. The photosphere is composed of solar granules. Solar granules are hot pockets of plasma, and that's how the star cools itself. Convection means that this hot plasma rises, and as it cools, it slinks to the side and then goes back under to be replaced by more cooling plasma. The reason the spots are darker is because they're cooler than the surrounding photosphere.
So why do star spots form? Star spots are caused by strong magnetic field lines piercing the surface of the sun or the star. There are two processes going on that cause star spots. One is flux freezing and the other is magnetic tension. Flux freezing is caused by Faraday's law of induction and Ohm's law. So we can treat the plasma as a conducting loop with nearly zero resistance, because you can imagine that the plasma is free electrons floating around. And Faraday's law says that an EMF in a closed loop is equal to the change in flux, magnetic flux through that loop. So if we have an R near zero, then that implies that our EMF is zero, because we can't have infinite current. So if our EMF is zero, then the change in magnetic flux through that loop or parcel of plasma is zero. It's constant. So the magnetic field lines are going to follow the plasma as it moves horizontally. The other process going on is magnetic tension. So what happens is, due to QV cross B forces, the magnetic field lines will act as a very taut rope or a string with a lot of tension in it. So not only is the plasma anchored to the magnetic field lines do not want to move. So the plasma cannot move horizontally, and as Ryan was saying, convection requires horizontal movement. So now we have convection that is suppressed. If convection doesn't happen, the surface cools and the surface becomes dimmer. That's how star spots form. So this summer we studied LO Pegasi, a star located in the Pegasus constellation. Why did we choose LO Pegasi? Well, LO Pegasi has a very large star spot, which is convenient for us to observe. It is also, LO Pegasi is viewable during the summer periods that we're here. And LO Pegasi has a very short period. It rotates 360 degrees in 10.15 hours, which is awesome.
And so the instrumentation we used was a 0.3 meter Meade-Schmidt-Cassegrain telescope. Our CCD camera was the model SBIG ST8XE, and we took photos through the photometric filters BV, I, and R. Once we had these photos, we needed to clean them up, or essentially remove the noise that was in these photos. You can see here how in the center of this photo, it appears brighter than on the edges. That's due to vignetting, and that's our first type of noise that we have to remove. The second type of noise is to remove all the grains of salt that appear to be on our image. That is due to dark current noise. That means that the electrons were excited thermally instead of due to the photons of light that were captured by the lens of our camera. Once we've cleaned these images, we next perform differential aperture photometry in our program called Mira Pro 7. This means that we put these circles around our stars and measure the brightness. The innermost circle counts the brightness coming just directly from the star, while the outer ring measures the brightness coming from the sky, mainly due to light pollution from our nearby city, Columbus. Once we have these two measurements, they're subtracted to give us a more accurate measurement of the brightness of the star. We then take that brightness and plot it versus the rotational phase to get these light curves.
So as Ryan was saying, we plot the brightness versus the rotational phase, which is just a fraction of the period, and we get this thing called a light curve. And as you can see from year to year, the brightness shifts up and down. average brightness shifts up and down. It's actually the lowest in our year, 2012. And the amplitude changes from year to year. It's actually very small for our year. Before we get into the explanation of that, I'll let you know that through Doppler imaging, we know that there's a star spot located on the pole of the star. So if you can imagine plotting the brightness versus the rotational phase of a star that has a near symmetric spot, the same area of the star is going to be covered throughout any point on the phase. So the light curve is going to be constant because it's going to have constant brightness. So it's going to look kind of similar to what we have here. So what this means is that this low amplitude implies that the star spot has become more symmetric about the pole. And also, the dimness of our star this year indicates that more of the surface is covered by a star spot, which in our case means that the star spot has grown. In the future, we plan to input these light curves into an algorithm created by Dr. Harmon, our advisor, and it will generate 3D images of the surface of the star. Thank you for listening.